And so I'm maybe 2/3 or 3/4 of the way through uh, grading the receiver equalization project and stuff. So, you should be getting those grades hopefully this afternoon or certainly this weekend, along with some feedback. I did want to maybe say a few things about it. Let's see. Let me share my screen. And is the audio coming across okay this time? I know last session it was a little messed up. Hopefully
I can hear you better.
Better. Okay, very good. Very good. Yeah, we had some bad storms the night before. In fact, there was a tornado less than a mile from my house. And yeah, I don't know if that had messed up the internet somewhere along the line. It didn't knock it out, so that's good, but whatever. I don't know. So glad it's better now. So I wanted to make a couple of points here. Is a lot of y'all use this bit error function, bit error, and that's great. It's really designed to pass in some array of numbers. It's doing the analysis at the bit level. I find it most intuitive to go ahead and pass in bit arrays and then do it from there. Although I think you can use this K parameter to kind of analyze it and that type of thing. Just also note that in MATLAB you can return multiple results, right? So some languages allow you to do that. Some of the more modern ones, kind of we went from returning scalar values to returning objects, and now a lot of languages allow you this type of construct. So you can return the bit error ratio directly using this type of construct. And let's see, do they show you an example of that somewhere? Maybe they don't. They're still calculating the errors, but so I'll show you what I did. You can use this int to bit function, and you can plug in a matrix, an array there, and then n as appropriate, and then specify that the most significant bits are arranged first, which is kind of the more intuitive way, and that's why it's defaulted that way. But so let's look and see how I approach this. I know we've looked at this a little bit before, but you see here, I go ahead and convert the into bits using since M is 16, K is 4, so I use that, and then I use this type of construct, right? So it will return the number of errors and the bit error rate kind of all in one shot. So you don't need to actually divide by the total number of bits and that type of thing. So it's just, you can always do these things kind of more from first principles, but that just kind of helps. Also, so it turns out that these raised cosine filters and a lot of DSP processing in these type of radio systems use multi-rate processing, right? So, when you first started looking at sampled data systems, you defined a maybe a capital T, said that's your period. You have a sample rate, maybe F sub S, something like that, and you assume that that's constant throughout the system. And certainly, we normally, almost always, assume that it's constant in time, right? So that if we have a sample rate of 1 megasample per second, we don't like change that throughout time. But it turns out it can change throughout your system, and we end up dealing with multi-rate sampling systems, and so that's typically done in a raised cosine type filter. And so in your system, you will generate your kind of baseband waveform, and then you will upsample it or interpolate it to achieve a much higher sample rate, and then convert it to an analog signal using a DAC, and vice versa. You may sample it at a very high rate and then decimate it afterwards. Now, that's beyond the scope of this class, so don't worry about it too much. But it turns out that this raised cosine filter by default uses a 8 samples output per input sample, right? So you get one input sample, and it's going to multiply the sample rate by 8, right? So, and then vice versa on the receive version, you end up decimating it by 8. Okay, so you have 8 input samples to produce 1 output sample on a receiver, right? So in between, you're dealing with a much faster sample rate than the kind of outer parts of that receiver architecture, right? So, oh, darn it. It annoys me when I have to work remotely. Okay. Hopefully we get the same session. Yes, we do. So that is why on the delay, we calculate the delay from using this mean of the group delay and the transmit filter, and the mean the group delay of the receive filter. And then that's at the upsampled sample rate. And then we divide that by 8 in order to align things correctly, right? So down here, some of you all applied the delay at the kind of RF signal level, and that should work. And in that case, you wouldn't divide it by 8. Your delay would be 80 samples at that sample rate, right? But since I'm applying it at the more baseband level, I'm applying it here. Okay, so all right, what else? So I calculate the delay. I also calculate like the transmit power for both the filtered version and a non-filtered version. And so in my case, some of y'all looked at the amplifier model and tried to compensate for the gain based upon the parameters of that amplifier model, and that should work. I didn't like really go in and debug anyone's code to try to figure that out. But in my way of doing things, I just kind of approach it more fundamentally. So I actually measure it, right? So I take that transmitted signal, in this case, it's the modulated signal, and I just multiply it element by element, right? So if you're not super familiar with MATLAB, if you take 2 vectors or 2 arrays, or a vector and a matrix, and you multiply them, and it's going to try to do that matrix or or vector type multiplication. But if you prepend an operator with this dot period, then it's going to do that element wise. So what this is going to do is it's going to take for each element in mod sig, it's going to multiply it by the other one. Okay, so technically I could have done a dot exponentiated to square type of operation. Either way, it's the same operation, right? So this is an element by element multiplication. So now we're going to end up with an array that's just as long, or a vector is just as long as mod sig, right? Then I'm going to take the absolute value of that because we're really looking at power. And then I'm going to take the mean of that. And then that's going to take the mean across that vector. And that should give me the mean power, right, of that transmitted signal. And I do that for the no filter version and the receive version. And then I calculate the gain. Well, the gain is in terms of amplitude, so I really need to take a square root. I could have done a square root up here, then we'd have a root mean squared type of thing, right? Remember that, RMS? You saw that in circuits too, I'm sure, right? So that's really what we're doing here, right? So then I take, in this case, the square root of the receiver power divided by the square root of the transmit power, kind of do the same thing, although the notation's getting a little squirrely here because this, I call it the transmit power no filter, but that's actually what's being received also. So because there's no filters involved in that situation. So anyway, so then I just divide by that gain and demodulate, and that makes sure everything's scaled appropriately. And it will, we don't need to worry about the delay at this point. You could factor it in as long as you do it right. I factor it in afterwards. And then what you can do here is you can display maybe the first maybe 25 bits of both the receive and the input, right? And I'm enclosing this in these square brackets that makes them both kind of makes this a n by 2 type of matrix, right? And then I can what I thought maybe it's did I call that input data? What did I call it? Okay, there's X there. Why didn't it like that? Oh, because I ran the error control one first. So let's try that again. I guess I could have just used the up arrow there. So, all right. So now we can kind of look. Okay, so I got 13, 13, 0. I can look down. Oh, look, there's a 13, 13, 0, 10. 10. So I can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 right there. So that's 1, that's 11. Right. Again, we're one spaced. And does that correspond to my delay? Yes, it does. Right. So if you, are struggling to get things aligned, use tricks like this to try to figure things out. Another thing is to make sure you're demodulating things. One of the things I found was useful is look at my min and max of X, and it should be 0 to 15 because that's how we created those using that random number generator with that spread. And then also look at your RX bits and make sure, because before I got the gains all worked out, I would see like the minimum of RX bits would be 5 or something like that. It's, that's giving me a clue that that demodulation process isn't working as expected, right? So, okay, hope that helps. I am, so you're working on, oh, all right. So first of all, a number of you haven't turned in this latest assignment. Keep going, keep at it, get that in. And then also there's the next assignment, which is the error control coding. I think I already went over that, so I'm not going to belabor that point. But then I will be releasing very soon one that deals with the source coding. We're not going to do the Limple Ziv. We're going to focus on just the Huffman coding. We're a little bit behind lectures, so I want to get caught up. So I'm just going to do a very simple source coding one. It was only one lecture anyway. You're going to be dealing with the Huffman Dick. So we'll create a symbol alphabet and then associated with some non-equal probable probabilities, right? And again, those should sum to 1. And you'll use this Huffman dict to actually create a dictionary of these, right? So that's actually doing all that calculation process that we went through on Tuesday. And it will also calculate for you that average length. It's kind of, I think we call it a rate, but it's going to give you the same type of thing. And then you can generate some symbols, a signal, source signal out of that symbol alphabet, and then we can use Huffman enco to encode it, and then we'll eventually do a Huffman deco to decode it, right? So also note that when you create this dictionary, MATLAB typically handles its dictionary type structures with cell arrays. So you may not have looked at these before. It's a little bit more advanced MATLAB topic. So if you haven't run across that before, a cell array is basically allows you to toss in any kind of data into it, right? So each cell can contain any type of data. It's still a collection, and you can kind of index into that collection like you would an array, but we're going to be able to store very heterogeneous type of data in that. Right? So that's a bit of a review. All right, let's dive into our lecture now. Unless anyone has any questions with any of that information. So I have not, I've started writing up that source encoding one. It's not visible to you yet on Moodle, but it will be shortly. So, all right, let's, all right, sorry, juggling windows on my screen here. So hopefully you can see this. Lecture 18, receiver noise analysis. This is ever so slightly out of scope of this course. It really leans a little bit more on implementation of your systems. But we talk about noise a lot, and we've talked about how signals are modulated to different frequencies and that type of thing. So this adds a lot of context. So hopefully this kind of fills in some of the blanks that you may have and all this understanding. So so we'll look at thermal noise and phase noise, and we've talked a little bit about this before. Then we'll go into noise figure analysis, and then also look at intermodulation distortion, and then combine those two into what we call a spur-free dynamic range. All right, so thermal noise, we've talked about this before when we first started this course. Recall that any circuit with resistance and above absolute zero produces a noise voltage due to the random motion of electrons moving in a resistance, right? So those electrons moving, what's that? We call that current, right? So as that current moves through that resistance, it creates a voltage. And here's a handy equation for that. We know that this K is Boltzmann's constant, and then we've got these, main thing here is the temperature and the bandwidth. So then let's see, do I have anything? Right. So this generally applies. It's again still a bit of an approximation, as we've talked about. Noise of this sort has a flat power spectral density, but that really goes up to frequencies that are practical for microwaves and millimeter waves and that type of thing. It does eventually have some roll off associated with it, and also there's some approximations that the temperature does not go too low, right? So you get down close to absolute zero, then you're going to need a more complex model to handle this. This is actually maybe the first term of a Taylor series approximation or something, right? So, all right, let's look at then the simplified RF radio frequency receiver front end, right? So, and we looked at that kind of communication system model where we got the source encoding, and then some channel encoding, and then modulation, and then the channel, and then we've got the receiver, kind of the reciprocal operations there, right? So that all that kind of happens from here on to the right? So, but in this case, we have some circuitry up front that allows us to get to the point where now we can actually have our receiver where we maybe integrate it and sample it, or we and then compare it to a threshold, or we're doing a maybe a match filter receiver or something, right? So let's start over here with the antenna. The antenna has finite bandwidth and possibly gain and corresponding directivity, right? So there might be some polarization involved and that type of thing, right? So sometimes we want something that's highly directive, and other times we want something that would be more omnidirectional or isotropic, so that we don't have to worry about exactly how we're oriented, right? So for example, a cell phone, a handheld cell phone, of course, you're always moving this. If that antenna was highly directive, that would cause a lot of problems, right? So sometimes it would be pointing towards the antenna, the base station antenna, and you get great gain. Other times it'd be pointing away and you would have terrible gain, right? So, but like, so you want a more omnidirectional in that case, or very low directivity. Conversely, if you've got a satellite system, your link budget is pretty compromised already, and so satellites don't actually have a lot of power to them, and it's a long distance, so we use much larger antenna apertures and create a lot of gain, right? So you may have touched on that in your applied fields, electromagnetic fields course, although antenna theory usually kind of comes after the basics. Then we'll typically have a very low loss filter at the RF level, and this is to protect the low noise amplifier inputs from strong interferers and the resulting intermodulation distortion, right? So you remember near the beginning of the course, maybe a few lectures in, we talked about we use these trig identities and multiple cosinusoidal signals and showed that if we go through a highly nonlinear device like a mixer, then we will end up with not only the original signals, but we'll end up with the frequency signals at frequencies that are the difference between them, and maybe the sum, and that type of thing, right? And maybe twice the frequency of signals and that type of thing, right? So we use that to advantage in a mixer like this, where we're going to take a local oscillator with low phase noise, and maybe we tune that so we can receive different stations, different channels, and we run that into this mixer that then creates these intermediate frequency results that are maybe the difference between the RF and the yellow, or the vice versa, the LO minus the RF. We know that there's other frequencies, but we'll tend to filter those out. But it also that also occurs here if we have not only our desired signal, but maybe we have some strong signals close by that then would cause this amplifier to go nonlinear at its input stage, and do some mixing also. And in that case, we call that intermodulation. So we're kind of modulating two signals, maybe two spurious signals that produce another spurious signal in band, or maybe interfering signal with our signal that causes some problems and that type of thing, right? So we want to be aware of that. Then we have this low noise amplifier. It's really designed to add minimal amount of noise to the system, and we'll have typically moderate gain. And this might be composed of multiple gain stages before we go to the mixer. There might be some other amplifiers here. We're going to show that the first one is critical, right? And so we already discussed the mixer. Then we've got a filter here. This IF filter, intermediate filter, is usually the one that actually selects a particular channel or station that we want to listen to, right, on our receiver. In a cell phone case, it would pick out a particular channel that cell phone is operating on versus others, or in, let's say, an FM broadcast receiver, it's going to pick out the station you want. It's got a 200 kilohertz a channel assigned to it, and there might be some distant stations in the adjacent 200 kilohertz slot that you want to get rid of, and then there might be some more close by ones that are kind of near. Also, we try to allocate things so that in a particular area you don't have stations right next to each other in frequency. But this is the guy that's selecting the station you want in here and rejecting all the others, right? And then we've got this. So a note here that this, in the old days, this is all analog. We use analog modulation and stuff. Then we switched to digital, but all the circuitry was still analog, right? And your sampling would be occurring down here. But we're tend to move the sample and quantization, or basically the analog to digital converter, the EECE, earlier and earlier in the process, right? And so even the local oscillator, the mixer, that type of thing, the goal is to get right up to the antenna and do all of this in kind of the digital world. But there's obvious challenges in building good enough ADCs to do that. But that's a trend. And then after that, your processing would be, if it's super high speed, it'll probably be done in firmware and a FPGA. But as you lower the sample rate, then you'll be implementing much of this in software on digital signal processing, GPUs and CPUs. All right, so then let's look at how we can quantify these things, right? So I said that this guy here is critical in setting the performance of this system. Why is that the case? Well, let's first developed this concept called a noise figure or noise factor. Right? So noise figure quantifies the noise added by a device. For example, an amplifier, a mixer, a filter, any type of component that's processing your signal, right? And that is, let's say an amplifier. Well, it's designed to amplify your signal, but it also is going to add a little bit of noise to your signal, right? And then if that noise is added at the input, then the amplifier gain amplifies that noise also, right? So, and the amplifier has some finite input resistance, so it's going to have some noise generated in that. That thermal noise is going to be generated as a voltage from the current that's impressed upon the input resistance of that amplifier. And there may be some other sources of noise inside the semiconductor stuff. If you've taken an advanced semiconductor course, you may have studied some of that. So we quantify this by measuring the signal noise ratio at the input and then the signal to noise ratio at the output. And then we form a ratio of these, actually two ratios, right? And then we call that the noise factor. So then we'll often specify that in terms of dB, and we tend to call it a noise figure at that point. Since it's a ratio, it's actually a ratio of ratios, it's dimensionless, right? So these are all the same unit. Signal and the noise are all dimension in units of power, as is the same at the output. So basically, we're looking at the signal noise ratio at the input, and then the amplifier adds a little bit of its own self noise and amplifies it, and then that means that the signal noise ratio at the output is typically going to be worse, right? Because we have a certain signal power, and maybe we have some noise at the input, but then we add some noise at our own input stage, and then we amplify it. But these are all amplified the same, right? So our signal noise ratio at the output, this noise is going to be larger relative to the signal than it is at the output. So this is going to create some degradation in our signal noise, right? So it's closely related to noise temperature. We won't really go into this, but if you study certain types of communication systems, then we would talk about things like noise temperature rather than noise figure, particularly in satellite communications. And so there's some conversions you can do there. Just note that you may see noise figure specified in dB or in linear units. You gotta make sure you're using the right form of that in any given equation, right? So a single stage low noise amplifier might have a noise figure of 2 dB, right? So that might be a typical number. It could be lower than that. Could be higher than that, right? And a gain maybe somewhere around 7 to 12 dB, maybe 15. Typically, if you're trying to get real low noise, then you're going to have to sacrifice a little bit gain at the same time, right? It's just one of those trade-offs that we have to deal with, right? So now filters. Typically passive devices, a passive filter, they will have a noise figure that's equal to their insertion loss, right? So if you got a 2 dB loss in that RF filter, or let's just use 3 dB, right? So if we lose half of our energy or power in the signal as it goes through that filter, then we'll have a 3 dB insertion loss, and then that'll be equivalent to our noise figure. Mixers, will typically have a little slightly higher noise figure than their conversion loss, right? So again, this is more at the circuits level, but when you stick in a signal here, then this is typically a semiconductor set of diodes, but it's passive. It's not amplifying typically. Or maybe I should say kind of old school. And therefore, there's going to be a little bit of loss through this. This signal's local oscillators usually pumped in at a pretty high level to switch the diodes off and on. That allows you to pass the signal and but create that nonlinearity. But so there's some conversion loss of the signal here relative to the signal here. There are different frequencies, but if we look at that signal amplitude or signal power, there's some loss in that process there, right? So, so it's got a certain conversion loss, but it's also going to have a little bit of additive noise, and so it'll have slightly higher noise figure than its conversion loss. Oscillators, not oscillators, right? So we have that oscillator down here, and this signal gets multiplied by this signal, and there's so if there's noise on this, or if there's noise on this, that noise can end up at the output, right? And but it turns out that oscillators are usually operating in a saturated mode. They're a positive feedback type system, and so that active device, let's say it's a transistor, is going to keep amplifying the signal until it compresses and actually enters into some level of saturation, right? And that is actually kind of good because that means the noise is kind of saturated also, right? So we usually don't have to worry about amplitude noise in oscillators, but because of that feedback loop is what creates that oscillation, right? And you probably looked at feedback systems and look at their stability and that type of thing, right? And in oscillators, we purposely create some positive feedback, which we're normally trying to avoid in amplifiers, right? But if there's any sort of phase change, like momentary phase change in that loop, that'll change the actual frequency at which the oscillator is oscillating at, right? So we can see that here in terms of phase noise. Oscillators vary about their ideal center frequency, right? Let's say this is ideal at 100 megahertz, right, on this spectrum analyzer display. And we'd like that oscillator to be what? It's a cosine signal. The spectrum of a cosine is a delta function, right? So it should be an impulse or a delta function right there, right? If we're just looking at positive frequencies. Then, but there's some, minute phase shifts over time, and they vary randomly. And so your frequency will change kind of instantaneously. And typically we'll have some energy here in its power spectral density, right? So you remember that from our probability and where we can take the Fourier transform of the autocorrelation of a signal, right? But we just look at that as a spectrum of the signal. And so we have this energy out here. Well, if we've got, let's say, an ideal signal here, this is our maybe one signal, but then there's another signal over here. That's a much weaker signal, but that phase noise is kind of covering it up, right? So a lot of hand waving going on here, but we want good phase noise. We want this to be way down here, right? And what we'll see is that the phase noise is typically high close to the central frequency, and then it decays. And we might expect that. It's usually maybe some complex tendencies out here, but even if we think of like a Gaussian type of process, then we would expect to maybe have our frequency fluctuations most of the time close to the central frequency, and then fewer or less often farther away. And so, all right. Now, once we've added noise, once you have noise added to your desired signal, it's hard to get rid of, right? So recall the matched filter type receiver. Then we talked about how that design of that match filter is it's designed to match the spectral shape of the signal, right? And to remove as much noise as possible without removing the signal, right? So we want to kind of optimally filter that signal, but then everything else we're trying to get rid of, right? Everything else is that noise. But once we've done that, you know, any other noise inside the bandwidth of that match filter, we're not getting rid of, right? Because if we try to get rid of it, we're going to get rid of our signal also. There's some signal processing tricks we can do, but kind of first order, we're stuck with it, right? So we want to understand, maybe look at this cascaded noise figure analysis. So how does our noise performance behave throughout our system? Understanding that it's only going to get worse as we go through, right? So every stage adds a little bit of noise, but its impact depends on how strong the signal is at that part of the receiver. When the signal is low, let's say right at the antenna, we haven't amplified it yet, right? The noise in the component is significant with respect to the signal, right? It's kind of relatively at that maybe same level, right? When the signal is high, maybe we've amplified it and it's now deeper in the receiver chain, then that additive noise at that input of that amplifier or other type of component is still kind of small, right? But meanwhile, we've amplified that signal. So the kind of impact of that additional bit of noise is much smaller, right? So the conclusion we're going to come to is that the low noise amplification, or amplification with where we're emphasizing low noise, is more critical in the early stages, right? So the idea here is we're not going to derive these equations, but if you look at a cascaded type system, maybe this is the RF filter, this is the amplifier, the low noise amplifier, this is representing the mixer, maybe a post mixer amplifier, that type of thing, right? So if G1 is large, then this factor and all these other factors get diminished, right? It's being divided by G, right? So then that means that F1 is going to dominate the overall noise performance of the system, right? And maybe F2 to a certain degree, but by the time we get to F3 here, it's being divided by G1 and G2, the combination of those gains, right? Since we're dividing and multiplying here, we're using linear units and all of these, right? But so the conclusion here is that the earliest stage, which the RF filter and the low noise amplifier, is critical in setting the noise performance of the overall system. So we want a very low insertion loss of that first filter, and then a very low noise amplifier at the beginning. So here's an example. We can look at an RF filter insertion loss of 1 dB. In linear terms, that's 0.79. We'll take the reciprocal of that because this is really kind of a negative gain. This would, the noise figure would be 1 over this 0.79, which should be 1.26. The low noise amplifier, now here, this is specifying gain instead of loss. So this is a positive value of plus 10 dB. Conveniently, that's a factor of 10, right? And noise figure of 1.5 dB, it's a pretty good amplifier. And in linear units, that would be 1.41. Then we're going to say that there's a second stage amplifier after this, and it's going to have a gain of 15 dB and a noise figure of 4 dB, right? So higher gain, but worse noise figure, right? So let's plug and chug. So we plug in this F number here, and then we plug in the noise factor for the LNA, divide by the gain. Actually, maybe that should be dividing by, I'd have to double check that. Since this is a loss, the gain is less than 1, so maybe the 0.79 is the one we should be looking at. And then dividing by these second stage amplifier, and we're subtracting ones here. It's just part of the formula. Again, we didn't derive this formula, we're just stating it. And then we add these up. Looks like I kind of combined some of these right away, and we end up with 1.97. So that's not as bad as, say, a second stage amp has a noise factor of 2.51, but we're actually ending up with a cascaded noise factor of 1.97, right? So it's dominated by those early stages. All right, now that's noise, but we also have some intermodulation distortion. So amplifiers, as we know, are only linear up to a point. After that, they start to compress. That gain curve, which is normally a straight line, then starts to bend over. That's why we call it nonlinear, because that line is no longer straight. It's no longer linear. And if we think about it, one of the conditions that we have on superposition that makes our life so easy in analyzing circuits, that no longer holds because it's not linear, right? Superposition, we assume that things are linear time invariant, and but they're no longer linear. So if you're doing a very sophisticated analysis, you'll maybe use what's called a Volterra series, which can model mild nonlinearities, and maybe I ought to put mild in scare quotes there, because mild is when, by the time you're using a Volterra series, you're dealing with a lot of nonlinearity, perhaps. And it's a series, and we include certain number of terms to it and that type of thing. If you're mild enough, small enough nonlinearities, then we can model it as like a power series polynomial, right? And maybe look at these first few terms, right? So this would be your offset, this would be your linear gain, and then this is your nonlinear gain. So we actually went through this earlier in the course, and we actually had a little test question on it, right? And we saw that if we go through enough trig manipulation, we'll have the sum and difference of frequencies and that type of thing, right? So if we have two signals at the input of our amplifier, then and at least one of those signals is strong enough to drive that amplifier into its nonlinear region, then we're going to generate additional signals at additional frequencies. And it's possible that some of these frequencies, yeah, they're offset from the originals, but in some cases, those can lie back in band where they'll cause you interference. So stated in this way, many of these signals are easily filtered out, but some lie in or near the signal passband in the subsequent filters, right? So we take advantage of this nonlinearity when we design mixers to shift frequencies, but and then let's say an LNA, strong signal is present at the input, it can drive it into saturation or nonlinearity, producing spurious frequencies. These additional signals interfere with our desired signal, right? So ultimately, we're going to do some sampling. We're gonna integrate and sample it, and maybe quantize the result, but we're actually integrating a interfering signal too, right? So it's going to cause us additional energy, which may or may not add. It might cancel, but it's going to cause some distortion in our constellation, reduce that usable distance we have. Same way, similar way as the noise impacted our ability to threshold our signals correctly, right? So here's a diagram of it, right? So if we have the input power on the x-axis, we have the output power on the y-axis, and we normally want to be operating in this region, but yeah, if we drive our input too high, we start compressing. We talk sometimes about a 1 dB compression point where we extrapolated this ideal linear performance out here and then actually measured where our gain is maybe 1 dB below that ideal gain, then we call that our 1 dB compression point, right? So ideally we're up here, but because we're starting to saturate, we're starting to compress or ultimately saturate, then our gain is not as much, and where it's 1 dB down, that's this as special point just because it's meaningful on a practical basis, right? It doesn't have magical mathematical value significance. It's just a practical type of thing, right? So we can refer this point to the power at the input that causes this compression, or we can refer it to the output. So we have an input intercept point referenced at 1 dB down, or we can have the output power reference there. And then, so as we've seen, we've got a situation where we've got maybe 2 signals at our passband, and then we'll have through that nonlinearity, we'll have twice that frequency, and we'll have twice this frequency, and we'll have the sum of those frequencies, right? We've looked at this before. We'll also have the difference of these 2 frequencies. Technically, we'll have some signals at DC also. And yeah, if the nonlinearity is big enough, we'll actually be tripling it and quadrupling it and so on, right? But the ones we're kind of interested in here is now there can be a let's say that this is first order, this is second order, right? Then we can have a third order effect that where let's say we have a doubling of W1 omega 1 here, right? But then omega 2, this signal then mixes with this one, and we end up with a signal there, right? And likewise, we start with this first order signal omega 2, then we end up with the second order signal at 2 omega 2, and then this signal at omega 1 mixes with this signal and creates this third order signal at the difference of this frequency and this frequency, which lies very close. You can do an analysis with this one also, and you'll see that they lie kind of on top of these others. So these signals can be in band, right? If your filter maybe is this wide, or maybe your operating waveform is pretty wide, but now you've got like two signals right next to each other. So these guys are the ones we're trying to avoid. So since we're dealing with a third order effect, first order, second order, third order, we can define what we call a third order intercept point. And what we'll see here is that we've got this linear response of our main signal producing our outputs, but then we also have this cubic response, or a slope of 3, right? So if this is a slope of 1, well, technically the slope is going to be its gain, but let's normalize out that gain for the moment. And so this linear response will have a slope of 1. The third order signals will actually have a gain with a slope of 3, right? So as you start to increase and you get into this nonlinear region, your spurs will start to exist, but initially they'll exist at a very, very low level, right? But as we continue to increase into that nonlinear region, then these third order signals will actually increase 3 times as fast as this signal will, right? So, but eventually we're going to compress, right? We're going to compress starting nearly the same place, right? And so what we do is we extrapolate both of these linear tendencies and find that since this has a much steeper slope, 3 times the slope, they're going to intercept out here at some imaginary point. This is, you're actually operating down here or down here, but this gives us a nice metric, figure a merit or metric for describing these mild nonlinearities. So where these two extrapolated lines cross, we call that our IP3, or third order intercept point. And again, we can reference that as the input intercept point 3, or we can reference it at the output intercept point 3. And both are used, so you got to be careful which one you're using in which scenario. So now we can again look at what happens as we cascade elements, right? So we might be cascading LNA with a subsequent stage, and it gets very complicated very fast, because now you've got all sorts of terms and stuff, but with some simplifications. In other words, mainly that well, first of all, the nonlinearity is kind of mild to begin with, so we can only use maybe that squared term that's creating this result, but that they're separated far enough in frequency that their phases don't line up, right? So phase in AC signal, you've got a phasor, it's kind of rotating at that frequency of that signal, right? And so if you've got two signals at different frequencies, those phasors are going to rotate at different rates. They're far enough away, you're going to be rarely, if ever, adding in phase, right? Most of the time you'll be adding more in a vectorial relationship, right? So that's what that condition is saying, and that's fairly easily satisfied. So now we add or cascade out these things using something that looks very similar to the noise factor analysis, but maybe in a reciprocal type of relationship. Again, noting that we can be dominated by that first stage. So other spurious signals we need to worry about: oscillators are often synthesized for lower frequencies and might be multiplied up by some factor n, another useful application of these nonlinearities, or maybe it's in a phase lock loop. It's more of an advanced topic. They can have all sorts of different spurs in their frequency spectrum, right? So these can also get translated into the IF signal band during that mixing process. So where does all this lead us? It leads us to the spur-free dynamic range concept. And that's all we'll really look at, is this on a conceptual basis. So the SFDR is the difference in amplitude between the desired signal and the highest spur. So we generally want to push the spurs down into the noise floor, right? So if we're dealing with a certain level of noise, maybe we've tried to optimize our system to push that noise down while we're amplifying the signal. But once a spur is in a noise, it's just all a bunch of all that energy down there anyway, right? So so that's the objective. So we want to minimize the noise and the spurs, but there is little need to over optimize the spurs below the noise floor, right? So now high linearity, so that's kind of the opposite of nonlinearity, right? So we want to develop a system that can have very high linearity. That's going to imply a very large device area, right? So if you're building a semiconductor transistor, whether that's in a integrated circuit, is more common these days, or if you're dealing with the higher power system, maybe it's still built out of discrete components to really get a lot of power, and therefore a lot of linearity. You need a lot of device area, and you also need high supply voltages, right? So once your output signal starts hitting that output voltage, depending upon the class amplifier you have, it's difficult to go beyond that, and you're going to saturate or clip, right? So you might use take advantage of some negative feedback, etc., right? But these tend to kind of run counter to developing a low noise amplifier, right? So it's non-trivial to simultaneously optimize for low noise figure and low intermodulation distortion. So if you go into communication system design and you're more of a circuits and systems kind of engineer, then this is your challenge right here, right? That's is what you get paid for. You do better at this, you get paid more, right? Well, in the ideal world, right? So, all right, so we can kind of augment this diagram now, and just note that at some point we've got a noise floor that we're dealing with, right? And so this spur-free dynamic range, we can look at what's the distance between our fundamental signal and where that spur, that third order intermodulation distortion spur, is just starting to come out of that noise, right? So now we'd love for those noise to be lower and lower, but this is kind of where we're stuck at, right? So this defines their spur-free dynamic range. In other words, at this point, and below, our spurs are under the noise level, right? So we want to optimize the noise level versus the signal, right? Signal noise ratio, but also the spur, and this is that kind of key metric in your system, right? When you've cascaded it all together, what is your spur-free dynamic range? And what this allows you to do is that by having a very high spur-free dynamic range, it means that we can receive a clean signal from a station that's very close to us, and also at the same time one that's very far away, right? And so that helps our dynamic range. So we need to be able to design our system so it can handle strong signals and weak signals at the same time. All right, so the RF filter is key to reducing the interferers that might cause intermodulation distortion, right? So let's get rid of them at that filter stage right away. Filters can have some nonlinearities, but they're usually much easier to deal with than amplifiers, right? So so we can filter those out to begin with, but you know, the better we work at trying to get rid of these, you know, nearby interferers, then we're probably going to have a trade-off with loss, right? So, so it's got to be very low noise, loss, or it will negatively impact system noise factor. The LNA is much more critical and therefore expensive than any subsequent gain stages, right? And because it's kind of setting your overall performance, right? It's dominating that. The others have a much decreasing impact on the overall cascaded results. Ultimately, the signal noise ratio, or maybe we refer it down to the bit level, the EBNO, that our receiver sees is as at that threshold device. So all this that we're talking about kind of happens before we really get to all right, what's that noise that we're, you know, dealing with in our modulation scheme, right? And so when we looked at the trade-offs between distance or Hamming distance and a constellation, and kind of showed that simple constellations like a BPSK or a Comm type thing, you know, a 4-level Comm, will have typically much wider distance and therefore can you know, have a lower error rate than, let's say, a 128 Comm or 1024 Comm or something, right? Where all those points are really close together and everything has to be perfect, or you're going to have errors, right? So all of this that we talked about goes into setting how clean is that signal at that receiver when you start to actually receive it. Okay, so all right, signal strength is determined by your transmit power, your transmit and receiver antenna gains, the distance between those, the path length as you propagate, your energy spreads out, and so your receiver only captures a small fraction of that. So there's a path loss that we talked about. Cables connecting your antenna with the rest of your system, both on the transmit and a receiver side, can be significant. If you've got a big tower and your transmitter's at the bottom, or your receiver's at the bottom of that tower, and the antenna's way at the top, you've got a lot of cable to run up there, right? And you see that both in a let's say you know, the towers you see at the side of the road, whether it's a cell phone tower, a point-to-point tower, or a broadcast tower. You also see it, let's say, on a ship where you know, you've got the radio room and the superstructure of the ship, but then you put the antenna up on a mast up there, right? So so then you also have polarization losses. If your antenna, most antennas are polarized in one way or another, it's vertically or horizontally or maybe circularly. If you have some mismatch between the polarization in your transmit antenna and your receive antenna, you'll have some loss. Now, all these are kind of more topics of your 311 electromagnetics course, or, you know, graduate level versions of these things, right? But that's what is kind of helping set the signal strength that you actually have when you start integrating things, right? When you actually start processing it in this system, right? Phase noise, you know, touched on this. You know, as you move away from the ideal carrier frequency, center frequency, that phase noise tends to decrease. But it decreases at different slopes. So if you go into oscillator design or system design, you're going to see that in some regions it's rolling off at 1/f Other cases, it's rolling off at 1 over f squared, 1 over f cubed, and stuff. So these can be important if you're doing an actual sophisticated system analysis, and this gets to be much more complex. Ultimately, it's all that energy gets integrated in the integrator of the receiver, right? So we're trying to get rid of it as quickly as possible. All right, so that's that. I've got just a few minutes, so I'm not going to start my next lecture, but I will preview it. So we will talk next week about spread spectrum. And this is basically when we looked at what Shannon says with that capacity theorem, right? So we have that capacity is equal to bandwidth times the log base 2 of 1 plus the signal noise ratio, right? And so given a certain amount of bandwidth, we can get a certain capacity. Normally, we don't want to use more bandwidth than that, but sometimes we do, and that's what spread spectrum is about. It's when we use sometimes a whole lot more bandwidth than what Shannon's capacity theorem says we need to. And we'll look a little bit why, that we can overcome some narrowband jamming that may be adversarial, or it may just be, what happens if we've, let's say, got two Bluetooth Bluetooth systems, or Bluetooth and Wi-Fi actually often operate in the same band. And so, both use spread spectrum to be able to avoid the interference of these other systems, right? And then it also has some impact in fading, where signals that take two different paths to get from the transmitter receiver have different path lengths, and therefore different phases, and can cancel out if they have opposite phase at the receiver. And so by using broader bandwidth, we can overcome that, because those cancellations are usually only over a very narrow bandwidth. So that's just kind of a preview, get you thinking. So I will finish the grading certainly by next Tuesday, and I think the error control coding is due on the 10th, something like that. We're going to go see the eclipse on Monday, weather permitting. It's actually totality is maybe an hour and a half or 2 hours away from us. So we're going to enjoy that. You guys will enjoy partiality a little bit later than us on Monday. So I hope it works out for you. I hope you have great weather, and we will otherwise see you next week.
Thank you, Professor.